understand why the current in short channel is less than the current in long channel.
Why the current in short channel is less than the current in long channel?
Yes, sir.
So
The
you're not able to
saturated
understand
current.
the velocity saturation wala concept. Am I right?
Uh, kind of, yeah. Yes, sir.
Hmm? So
हाँ
let us look
मतलब
at it again.
आई
हाँ
कैन
बोलो.
से लाइक इलेक्ट्रिक फील्ड एक पॉइंट पे इतनी ज़्यादा बढ़ गई सो
Hmm.
वेलोसिटी सैचुरेट हो गई
Hmm.
लेकिन दोनों में हो रहा है ना वो तो सर लॉन्ग चैनल में भी हो रहा है शॉर्ट में भी हो रहा है तो फिर इसलिए आई एम लिटिल बिट कंफ्यूज
Okay. So let me.
Sir, sir,
हाँ.
sir, I just wanted to add to this doubt if you can continue. Sir, can you also tell why sir, the mobility also degrades due to vertical field and it is dependent on gate voltage. So, but we are
नहीं,
also
दोबारा से
talking,
दीपांक तुम्हारी आवाज थोड़ी सी क्रैकल कर रही है तो दोबारा से बोलो एक बार.
sir, I haven't metro में पाँच मिनट था. I will tell. You can continue with your. Sorry, sir.
नहीं नहीं बोलो क्योंकि मैं कर ही रहा हूँ तो फिर आई विल आंसर कॉम्प्रिहेंसिवली ना.
सर my doubt was that कि mobility भी degrade होता है because of gate voltage due to vertical field और saturation में क्या मुझे मेरा डाउट था कि जब हम saturation बोल रहे हैं velocity क्या उसका कितना इफेक्ट है एक्चुअली जब हम सिर्फ VDS की बात कर रहे थे velocity saturation में बट दोनों चीज़ें उससे हो रही है ना वो मतलब सर I am unable to frame my doubt. I'm sorry.
तो
वेट सॉरी सर ठीक है आप समझा रही आई लास्ट अगेन
these are two devices. Let us say that one is a long
यस
channel device, one is a short channel device. You put the source on ground and you put the drain on, let us say, 2.5 volts. Is that okay?
यस सर
Over here again, we put the source on ground and we put the drain on. We say that scaling over here, so we put the drain on 1.2 volts. Okay, let us say this is 180 nanometer and this is 60 nanometer. करें इसको चल 2.5 की जगह let us put it as 2.4 just for the ease of calculation. Is that okay?
यस सर
So what is the lateral electric field over here? 2.4 over 180. Some volts per centimeter कुछ आएगा. ठीक है. तो अगर मैं इसको जस्ट वो करूं तो ये आ जाएगा 0.4 by 6 से डिवाइड कर रहा हूं बेसिकली मैं 30 तो आ जाएगा लेट अस से 0.00133. Am I right?
यस सर
नहीं 0.001 नहीं 0.0. ठीक है. What happens here? हमने कहा 1.2 डिवाइडेड बाय 60. ये क्या हो गया
0.02
0.02
यस
है ना. तो अब आप देखो कि मैंने यहाँ पे 2 जीरो तो नहीं थे ना, एक ही जीरो होना था. क्या हो रहा है यार
0.013 था सर ये
0.013.
यस
सो मैंने वोल्टेज भी कम करी, सब कम करा. लॉन्ग चैनल डिवाइस में फिर भी जो मेरा इलेक्ट्रिक फील्ड है वो कम था और यहाँ पे ज्यादा था.
यस सर
ठीक है. हमने वहां पे कहीं पे देखा था कि 0.015 के आसपास कहीं पे देयर वाज सम नंबर लाइक, ये तो मैंने रैंडम कुछ भी ले लिए हैं, बट इन बिटवीन समवेयर देयर इज दिस पॉइंट ऑफ वेलोसिटी सैचुरेशन.
यस सर
है ना. तो अब यहाँ पे क्या हो रहा था, यहाँ पे अभी जैसे जैसे आप इलेक्ट्रिक फील्ड बढ़ा रहे थे तो क्या हो रहा था, आपका पिंच ऑफ हो रहा था. ठीक है. आपका इलेक्ट्रिक फील्ड बढ़ाने के बाद आपका पिंच ऑफ हो रहा था, लेकिन द स्पीड ऑफ द इलेक्ट्रॉन्स एवरीवेयर वाज इंक्रीजिंग कंटिन्यूअसली. या अगर पिंच ऑफ से भी पहले की बात करें, लीनियर रीजन की बात करते हैं, कि अभी आप लीनियर रीजन में हो, VGS जो है वो यहाँ तो नहीं, VDS इतना हाई है तो वो लीनियर में नहीं हो सकते, तो पिंच ऑफ हो चुका है यहाँ पे, तो पिंच ऑफ हो चुका है यहाँ पे, लेकिन जो स्पीड है, क्योंकि अभी वेलोसिटी सैचुरेशन नहीं हुआ, आपने जब VDS बढ़ाया तो स्पीड बढ़ती रही,
यस सर।
ठीक है। तो जब आप सैचुरेशन में व्हाट डू यू से, जब आप सैचुरेशन में एंटर करें, एक्चुअली हम गलत जगह से शुरू हो गए, हमें गेट को बढ़ाना चाहिए और फिर देखना चाहिए कि क्या हो रहा है। सो लेट अस से सैचुरेशन करंट कैसे आता है, इसको हम अभी 0.6 पे चले जाते हैं, तो ये क्या हो जाएगा, 0.003 समथिंग, 325, ठीक है। हम इसका 0.6 का करंट देखते हैं, ये हो जाएगा 0.01, ठीक करा है मैंने।
हाँ यस सर।
हम्म। तो अब 0.6 वोल्ट पे जब मैं लीनियर से, मतलब मैं VG, जब मैं कह रहा हूं कि मेरा गेट ओवर ड्राइव जो VGS माइनस VT है, वो गेट ओवर ड्राइव समथिंग लाइक 150 मिलीवोल्ट के आसपास आ गया, एंड दैट इज वेयर माय सैचुरेशन स्टार्ट्स टू हैपन। हाँ, उस
यस
पॉइंट
सर।
पे देखते हैं कि इधर क्या इलेक्ट्रिक फील्ड है, 0.00325। एंड उस पॉइंट पे यहाँ पे क्या इलेक्ट्रिक फील्ड है,
0.01।
यू सी द डिफरेंस।
हाँ यस
तो
सर।
इसमें क्या हुआ, इवन व्हेन यू रीच दैट वी सैट वाला कंडीशन, जहां पे आप सैचुरेशन में एंटर करते हैं, आपका इलेक्ट्रिक फील्ड रीजनेबली लो था।
यस सर।
तो क्या हो रहा था, आपका भी पिंच ऑफ शुरू भी नहीं हुआ। जब तक देखो, पिंच ऑफ जब शुरू होता है तो आप सैचुरेशन में एंटर कर जाते हो,
यस सर।
इतना क्लियर है। तो अभी आपका
हाँ
पिंच ऑफ शुरू नहीं हुआ था, अभी आपका खाली ये चैनल के अंदर इलेक्ट्रॉन डेंसिटी बढ़ रही थी एज यू आर इंक्रीजिंग VGS, you're getting more and more electrons and more charges in your channel region, inversion layer. That was what was happening. Are you with
यस
me?
यस सर।
ठीक है। तो आप एक लॉन्ग चैनल डिवाइस में पूरा अपने सैचुरेशन कंडीशन तक आने तक, क्योंकि तब तक भी वेलोसिटी सैचुरेशन नहीं हुआ है, आप बहुत कम इलेक्ट्रिक फील्ड पे हो, आप वहां पे अच्छा वो देख पा रहे थे, आप एक्चुअली करंट का एक पूरा इंक्रीज देख पा रहे थे लीनियर रीजन में,
यस सर।
ठीक है। अब आप शॉर्ट चैनल डिवाइस पे आओ, लेट अस से जो वेलोसिटी सैचुरेशन है वो इन दोनों के बीच में कहीं पे होता है, लेट अस से वो 0.006 पे हो जाता है, लेट अस से,
ओके सर।
ठीक है, अंडरस्टैंडिंग के लिए कह रहा हूं।
यस
तो
सर।
अब क्या हुआ, जब आपने यहाँ पे आप यहाँ पे शुरू करे 0.1 से, तो चैनल बना 0.2 से, 0.3 से, आप धीरे धीरे करके बढ़ते गए, ये 0.0, 0.001, 0.002, 0.003, आपका चैनल, आपके इसके अंदर डेंसिटी आती रही, इलेक्ट्रॉन्स की डेंसिटी आपकी बढ़ती रही, ठीक है।
यस सर।
बट सून व्हाट हैपेंड, सून यू हिट दिस वैल्यू।
हाँ
When did you hit this value? You hit this value when you were only at, let us say, 0.25.
यस सर।
0 point नहीं, इसी के हिसाब से अगर देखें तो you will hit this value at something like 0.33, something like that, है ना। 0.6 का
यस
आपको 60% लेना है, 0.36।
पॉइंट या
सो एट 0.36 यहाँ पे तो आप पूरा 0.6 तक अपने करंट को बढ़ाते रहे, लेकिन यहाँ पे क्या हुआ, 0.36 तक आप पहुंचे तो आप इस पर हिट कर गए। वेलोसिटी सैचुरेशन होने के बाद अब आपका करंट बढ़ ही नहीं सकता, बिकॉज कॉलिजन हो रहे हैं इतने सारे कि अब
कोलिजन्स
आप
हो रहे
एक्स्ट्रा
हैं। हाँ
चार्जेस डाल ही नहीं पा रहे हो।
यस सर। यस सर। हाँ मतलब हम वहां तक पहुंचे ही नहीं।
हाँ,
ओके ओके
तो इसीलिए अब आपका सैचुरेशन यहाँ पे आ गया।
ओके ओके ओके। नाउ इट इज वेरी मच क्लियर।
Sir,
ठीक है, हाँ जी।
यस
so
सर।
sir, can we say like that key in the long channel, the pinch off and the VSAT was basically related, but now in the short channel, pinch off is happening much before the VSAT. I could achieve that. So the VDSAT has reduced.
या यू कैन से दैट।
But I mean, then when you go to the short channel, that VDSAT, that the VSAT and the pinch off kind of relationship is getting disturbed, right? Because of short saturation.
या
Okay, right.
ठीक है.
Sir, in short channel devices, the critical electric field is achieved earlier. That's it. That
Yes, because of shorter length and voltage not scaling at the same rate.
Yes, sir.
Both things are happening there.
Yeah, okay, okay.
है ना. देखो, और
Yes.
वोल्टेज भी मैंने जिस तरह से मैंने लेंथ 1/3 करी, वोल्टेज भी 1/3 कर दी होती, और मैं जो सैचुरेशन वोल्टेज है मतलब वीटी को भी उतना कम कर दिया होता कि मेरा 150 मिलीवोल्ट्स अब वीटी जो है वो सेम हो जाता, वो भी 1/3 हो जाता, तो मैं अलग ही जगह पे पहुंचता ना.
हाँ. Yes, sir.
बट द थिंग इज, first thing, that 156 kT by Q above VT, that 150 millivolts is constant. That is a property of silicon. With scaling, you cannot change that. Even if you reduce the VT, that 150 millivolt will anyways get added up, which is not changing. So that is the reason why you are actually not able to, or that is the reason why you're hitting velocity saturation very fast.
Yes, sir.
Okay.
So what was the 150 millivolt that you mentioned just?
Oh, so VT से, so saturation condition जो कही जाती है, that is typically understood to be 150 millivolt, 6 kT by Q above threshold voltage. 1 kT by Q is around 26 millivolts at room temperature. K पता है ना आपको? K, what is K?
Yes, sir.
Boltzmann
Yes,
constant.
sir.
Yeah,
Yes.
boss.
हाँ, temperature, absolute temperature, T by Q. Q is the charge of one electron.
Okay.
1.6 into something raised to power minus something electron volt. So 1 kT by Q is equal to around 26 millivolts at room temperature.
Okay.
You say a device is deep into saturation or fully into saturation when you are 6 kT by Q above threshold voltage.
Okay.
That is approximately 150 millivolts. Otherwise, you call that operation as near threshold region of operation.
Okay, sir. Okay.
Okay. Yes. What next?
Sir, can you explain that high frequency, low frequency inversion thing? Sorry, sir, it is asked repeatedly, but
No. It is not about sorry. अगर नहीं clear हुआ, इसका मतलब मैंने clearly explain नहीं करा ना अभी तक. Why do you worry? Any question you have, you should ask. I want you guys to have full clarity on various topics. So even if, see, in the class, I can repeat something only X number of times because I have a syllabus of DVD to cover. And this is unfortunately not a part of DVD, however interesting it may sound to be. This is part of SSD. So I have to somewhere say कि भाई class में इतना, and then office hours or outside the class we discuss more, है ना? But please never hesitate to ask questions. The purpose of office hours and these contact hours is that you get full clarity on stuff. So what are we saying? We are saying that,
Sir,
yes,
please explain it with the diagram of electron flow also.
diagram of electron flow. What is electron flow?
Sir, I mean in the MOS capacitor, high frequency, low frequency in this question with the electron flow diagram.
Okay. इलेक्ट्रॉन फ्लो डायग्राम कौन सा था, वही तो बोल रहा हूँ. ये तो कैपेसिटेंस की वैल्यू आ गई.
Sir, from where electron are going and from where they are not able to go.
Okay.
I want.
So let us draw the MOSFET like this. This is my poly, this is my oxide, and this is my silicon. ठीक है? Is it okay? I can rotate it now. Hello, I can rotate it. Nahin.
Yes, sir. Yes, sir.
So now, how does the band diagram look? Band diagram looks like, let us say this is the Fermi level. So gate is at the Fermi level only. Then we talk of oxide. Oxide is 3.1 electron volts above there. Then we said that the dielectric constant of the oxide is 3 times that of the silicon. So whatever is the inbuilt voltage, उसका 2/3, उसका 3/4 यहाँ drop करेगा, and the remaining will drop in. So the remaining will drop in the silicon region. ठीक है? Is it okay? Can we show it like this? थोड़ा सा Is it okay? Hello?
Sir, 3/4 will drop in the silicon dioxide region, you said.
So, yes, because the dielectric constant of this is something like 12 and this is something like 3. So, this will show 4 times drop. No, 3 and 4, पता नहीं कुछ. There is this ratio.
3.9 सिलिकॉन डाइऑक्साइड का होता है और 11.7
तो 4 का रेशियो है ना? 3 का रेशियो है. सो 3 का रेशियो है, मतलब दे विल बी टोटल. अगर मेरे को x का ड्रॉप करना है तो 3/4 will drop over here and 1/4 will drop over here. The slope over here will be 1/3 of the slope over here. That is what the ratio of dielectric constant means, na?
Okay, sir.
हाँ. So the slope की टर्म्स में बात करते हैं. कहाँ पे कितना ड्रॉप हो रहा है वो नहीं करते, स्लोप की टर्म्स में बात करते हैं. This slope is 3 times the slope you will have here. Okay? कहाँ पे कितना ड्रॉप हो रहा है उस पर नहीं जाते. But what we are sure is that this is also 3.1 electron volt. Okay? Are you with me till now?
So that means the difference between the conduction band on the substrate and the dielectric is 3.1.
So the barrier of oxide from any silicon is 3.1 electron volt. We had silicon on the gate side, so it is 3.1 electron volt here, and we had silicon on the body side also, silicon side also. So we have 3.1 electron volt there also.
Okay, sir.
Okay, that is the barrier height of oxide. You cannot change that.
Okay, sir.
So now what happens? Now you say that, so over here I've already shown the inversion condition. Are you able to see this? I've already shown that अगर ये phi है, I've already shown कि यहाँ पे भी almost phi वाला है. Are you able to see this? I've already shown an inversion condition over here.
Yes, sir.
So now let us say that we are operating at a very low frequency. And okay, so यहाँ पे एक ये भी mention कर देते हैं. This is my WD max. Is this clear?
Yes, sir.
भाई acknowledge करते जाओ, नहीं तो I will have to wait. So,
Yes, sir.
So what are we saying? At low frequency, what happens? At low frequency, I changed the gate voltage very, very slowly. Very, very slowly. So what happened? Electrons which were there in the inversion layer.
Sir, you are not audible.
I'm not audible.
No, sir, you are audible.
No, sir, you are audible.
Okay. So I changed the input, the gate voltage very, very slowly, like a very slow frequency. Let me show it as a proper sinusoid. Let us say this is a very slow sinusoid. So what happened? The gate had a very slow sinusoid. So when the voltage over here became negative, let us say, at that point of time, it started to push the electrons from this inversion region away. And as it started to turn negative, electrons started to slightly drift away. Drift away means they would go into the substrate. Then when this starts to go positive again, then electrons come back. Are you able to see this? Low
Yes, sir.
frequency.
Yes, sir.
So what is happening? Where is the charge? So when I brought about a delta V on the gate, where did charge change happen on the on the silicon side? What was the spacing? So this was one plate. Where was the other plate?
Interface.
This place after TOX. Am I right?
Yes,
Yes,
sir.
sir.
So since it was at Tox, my capacitance went up again.
Sir, can I ask something here?
Yes.
So if there was a change after TOX, like at the inversion layer, so you said that the electrons will move away from that inversion layer, right? When we
Hmm.
have a negative polarity on the gate. So,
Hmm.
but the depletion region will still exist because we have an inversion layer and we have a p-type substrate. So a depletion
Yes.
layer will also exist in the body.
Yes.
So, sir, those electrons will they not affect the other end of the depletion region
No.
because they're moving towards it?
No. What they will do is, see, that is where inversion has happened. What does inversion mean? Remember, I said that inversion sets in after there is WD max. Depletion width cannot grow beyond WD max.
Sir, I'm not
And
saying it will grow. Sir,
wait. So since depletion region doesn't grow beyond WD max, any increase in voltage beyond uh, threshold voltage means that there is only extra charge that comes in the inversion layer and no change in depletion layer happens. So now what you are doing is, when you are giving this small signal at a very low frequency, you're just removing that extra charge. And still depletion layer will not change. Because of inversion region में हो, you are, let us say, how much above VT? 150 millivolts. You're deep into saturation. मतलब saturation मतलब जो भी यहाँ पे saturation की बात नहीं आती, but you're really deep into an inversion region. So see, I did not change the band bending here. Did I change the band bending? No, I just changed the charge. Is the low frequency curve clear?
Yes, sir. So then if the AC signal is towards positive, then like more electrons will be attracted
Yes,
towards
so they
the
will come. So
phase.
those new electrons will come from here.
So again, the charge change is taking place at the interface, so it acts as the bottom plate.
Yes.
Sir. Thank you, sir.
Okay.
Oh.
Now let
Sir.
us answer. Yes.
Sir, the reason that we are talking about here about charge variance as according with the frequency of the signal, gate signal. Sir, in one of the slide of MOS capacitance, when we were talking about three different regions of capacitance: depletion, accumulation, and inversion. You, sir, one of the slide contained the term DC and AC in the depletion region, like the lower layer of depletion region was it was
Sorry.
written that it is, sir, in the lower layer of depletion region, lower part, in one of the slide it was written as AC. So the reason for that is same like as we are discussing here.
I do not exactly remember the slide, but this is what we mean by high frequency and low frequency capacitance, because frequency will only come when we have an AC signal. Am I right?
Sir, in one of the slide it was written AC in depletion region and DC also. So
I mean, sir, he's talking about the slide, sir, in which slide we had the inversion layer form and then we had the depletion bit. So at the depletion boundary, there was this AC notation, and at the inversion layer, it was the DC written basically notation. So he's maybe asking about that, sir.
So their source also was included.
So that was for a MOSFET. We are talking about MOS capacitor.
No, sir.
अगर source included था तो वो MOSFET की बात हो गई.
No, sir. It was you in one of the slides you talked about it MOS capacitor when we were talking about accumulation, depletion, and inversion. I can show you the slide.
No. I have the slides. You don't need to show them to me.
Yes, sir. In the inversion slide, so in the inversion diagram,
Yes,
there
actually,
was a depletion
right now.
depletion bit, and at the depletion boundary, there was
Yes,
this
sir.
AC written, and the inversion layer was pointed as DC.
एक मिनट रुको. Let me open the slide now. अभी आप लोग बातें करो, मैं relate ही नहीं कर पा रहा कि slide को मैं क्या लिखा था.
Sir,
it was page number six.
sir, I
Page
have
number
the
6.
slide opened.
I
can share my screen.
have. रुको.
भाई एक करके बोलो, एक एक करके यार.
So let me show it to you. You're talking about this slide. And you're saying this is DC and this is AC. ये आप बात कर रहे हो?
Yes.
Are you able to see my screen?
Yes, sir.
So you're talking about this AC and this DC.
Yes, sir.
Okay. So अच्छा, और यहाँ पे DC and AC दोनों लिखा है. So DC actually does not really mean DC in terms of static current, static voltage. This over here means low frequency.
Okay, sir.
Okay, this over here means low frequency, and AC means high frequency.
Okay, sir. Sir, the explanation for the for this is same like as we were discussing.
Yes,
Okay, sir.
that is what we are discussing.
Sir,
Mhm.
sir, I have a minor doubt. Like when we are talking of inversion and depletion, like when we are moving towards more positive voltage,
Mhm.
then the inversion layer forms at the interface between SiO2 and silicon,
Hmm.
and then we have the depletion region.
So depletion region will be formed first, and inversion layer will set in later.
So it is within the depletion region, like
So
we count it.
so देखो, जो इन depletion region की बात करें तो एक region हो जाता है.
हाँ जी.
We are talking about inversion layer, so it is not in a region; it is at the surface.
Just at the surface.
Yes.
Okay. Okay.
सर एक डाउट है इसी पे.
Sorry.
हेलो सर, एक प्लीज डाउट है सर इसी पे, इसी कॉन्सेप्ट पे. सर हम लोग जब मैक्सिमम डिप्लीशन विथ पर डिफाइन करते हैं तो वो होता है 2 एप्सिलॉन बाय क्यू सरफेस पोटेंशियल बाय एनए, जो फॉर्मूला होता है.
हाँ.
सर उस केस में क्या होता है, डिप्लीशन लेयर के अंदर सरफेस पोटेंशियल फर्मी पोटेंशियल के इक्वल होता है, ठीक है. बट सर जब हम इन्वर्जन की कैटेगरी में आते हैं तब सरफेस पोटेंशियल ट्वाइस ऑफ फर्मी पोटेंशियल हो जाता है ना. तो सर अगर आप उसी वैल्यू को मैं अगर फॉर्मूला में पुट करूंगा तो वो एक एक्सजेड
वैल्यू आ जाएगी,
या एक्सजेड की वैल्यू आ जाएगी. तो सर इसका मतलब ये है कि वहाँ पे कुछ उसकी थिकनेस भी होती है, बट हम तो शीट की बात कर रहे थे, वहाँ पे एक शीट है केवल.
नहीं, तो डिप्लीशन लेयर की विड्थ की बात हो रही है ना.
नहीं, बट सर इन्वर्जन के केस में सरफेस पोटेंशियल डबल हो जाता है ना फर्मी में.
हाँ,
तो वो
सरफेस
जो
पोटेंशियल डबल होता है. तो डिप्लीशन विड्थ का फॉर्मूला बता रहे हो ना आप मुझे, या आप इन्वर्जन लेयर की विड्थ का फॉर्मूला बता रहे हो?
सर डिप्लीशन की बता रहा हूँ. तो सर उस
हाँ,
केस
तो
में
डिप्लीशन विड्थ मैक्सिमम हो जाती है. तो डिप्लीशन विड्थ वही तो हम WD मैक्स की बात कर रहे हैं.
मतलब उस केस में फिर वो 4 एप्सिलॉन बाय क्यू करके आएगी, जो आएगी पूरी,
जो भी आएगी, दैट इज द मैक्सिमम डिप्लीशन विड्थ.
मतलब उसका उस इन्वर्सन से कोई रिलेशन नहीं है. मतलब बस इन्वर्सन के केस में बस वो डबल हो जाता है फर्मी लेवल, वो डिपेंडेंट फैक्टर है ऊपर से.
अब इन्वर्जन के बाद आप जितना मर्जी वोल्टेज लगाते रहो, डिप्लीशन विड्थ वही हो जाएगी फिक्स, क्योंकि बाकी सारी चीज बस उस लेयर में एक्स्ट्रा चार्ज डालने की बात करेगी. वही एक्स्ट्रा चार्ज कमती बढ़ती होता रहता है अगर आप लो फ्रीक्वेंसी पे ऑपरेट करते हो तो.
अच्छा, केवल लो फ्रीक्वेंसी पे.
ठीक है, क्योंकि लो फ्रीक्वेंसी पे वही एक्स्ट्रा चार्ज कमती बढ़ती होता रहता है. तो वी से दैट माय इफेक्टिव डाइलेक्ट्रिक थिकनेस इज Tox and my effective dielectric constant is epsilon of silicon dioxide. ठीक है, so my effective capacitance is very high.
ओके सर.
ठीक है, is this clear? Low
Yes,
frequency is clear. Everyone, anyone has a doubt? Okay, so if we say that this low frequency is clear, then now let us look at what happens on high frequency. So one thing that you would appreciate is that electrons have to move in and move out from the edge of depletion, because in the depletion there is no movable carrier available now. So electron has to move out and in from edge of depletion region. Even if it is at a low frequency, electrons will move from there, but charge change will happen here. That is what we are talking about. Are you with me on this?
Sir.
Yes. Huh? So now what happens when we are talking about, let us say, high frequency? So at high frequency, there are electrons over here which want to move out, But what is the curve? Something like this. So electron negative की तरफ voltage गया, electron starts to move out, but before it actually moves out, before it just reached here, yet what happened? It became positive. So this electron came back here. So effectively, there was some electron movement that wanted to happen from the inversion layer itself, but it can't happen now. Because electrons are actually just staying here only in this region itself. The charge is not changing here. This charge is constant. But charge is changing on this plate. So charge change has to happen on the silicon side also. So where does that charge change happen? That charge change happens here because an electron, so when you applied a positive voltage, electron wanted to come from here. It wanted to come from here, but it could not come. Before it could come, there was a repulsive force, so it went out. So charge change actually happens here. So because charge change happens at the boundary of depletion layer, and that was where your minimum capacitance was, your capacitance, even if you operate at a higher bias voltage, remains low. Let us say that this arrow length represents movement of electrons, the time it takes to move the electrons. At low frequency, I am able to traverse this trajectory in every cycle. At high frequency, I have only this much of time available to me. I have no mobile carriers in this region, so this arrow cannot go anywhere here. This arrow can only be here. So any change in electron density or any change in these carriers would happen only at the edge of depletion layer.
Okay, sir.
यहाँ वाला इलेक्ट्रॉन जा ही नहीं पाता है बाहर, वो बाहर जाने की कोशिश करता है तो it is pulled back again before even it moves a little bit out. So all electron change, all charge change happens at the edge of the depletion boundary. Are you able to see this?
Hi, sir.
Any questions?
Yes, sir. Sir, in the inversion region, like if we are increasing at high frequency, there is no change in capacitance. But in low frequency, capacitance is changing. Sir, in low frequency voltage, like we have, if we are applying like sinusoidal wave also, we have both positive and negative voltage applied. So why capacitor is increasing only, not decreasing from here?
So see, we're talking about, so जो ये आपका x axis दिख रहा है ना, ये जो x axis दिख रहा है, this is your V bias.
Okay, sir.
Okay, and this thing that I showed over here, that is your V small signal.
Okay, sir.
So this could be 1 volt.
Yes, sir.
And this could be just 20 millivolts.
Yes, sir.
So we're talking about just 20 millivolt fluctuation.
Yes, sir.
Capacitance negative जाने की बात कहाँ आई?
सर क्योंकि पॉजिटिव तो जा रहा है ना सर, ये मतलब चेंज हो रहा है तो किसी भी डायरेक्शन में हो सकता है.
नहीं, अच्छा, तो आप कह रहे हो कि ये कैपेसिटेंस इससे नीचे क्यों नहीं जा पाता?
सर
क्योंकि WD मैक्स आ गया ना, WD मैक्स से कम ज्यादा विड्थ हो ही नहीं सकती डिप्लीशन रीजन की.
ओके सर, ओके. यस सर.
Is it clear?
Yes, sir. Yes, sir.
Okay.
Sir.
Yes, Gaurav.
At AC signal at low frequency, will the MOS capacitor will continuous toggle between accumulation and inversion mode?
नहीं, मैंने अभी क्या बताया? What you're talking about is small signal movement, है ना? We said the bias voltage is 1 volt, but it is only moving by plus minus. So it is only moving between 980 millivolts to 1020 millivolts.
Okay, sir.
So that doesn't guarantee an accumulation region, na?
Yes, sir. And sir, I asked the other question in class also, but sorry, I'm not getting. Let us assume the capacitor is under depletion mode. Okay, so there is a very much I think negligible inversion layer.
So you're talking about somewhere over here. You're talking about this region. अभी
Yeah,
inversion
yes, sir.
set नहीं हुआ है.
Yes, sir. At
In fact,
depletion,
depletion would be somewhere here. Okay, let us
yes, sir.
say it
At
like that.
depletion, there is no inversion layer, and then I applied the high frequency AC signal. Then will the capacitor undergo any inversion mode or not? Because charges are not able to come under
So see,
inversion
look at
layer.
it like this. AC signal is only 20 millivolts up and down.
Yes, sir.
So what will happen to the charge? मतलब, can 20 millivolts take you towards inversion?
No, sir.
No. Then how can inversion layer happen?
So basically, at high frequency AC, if I apply, there will not be inversion.
So in this entire region, because there is no concept of an inversion layer, there is no change in response for high frequency or low frequency.
No, sir. I apply means I change gate voltage at a higher amplitude also.
No. But हम देखो. So in VLSI or circuit analysis, we talk of a bias point, and we talk of the small signal AC.
Okay, sir.
So what is your bias point? You told me that the bias point is in the depletion region somewhere here.
Okay, sir. Okay.
The small signal AC is only 20 millivolts up and below this.
Means we basically could talk about first bias point, then after
Yes.
that.
Bias point is always the first mainstay.
Okay, sir.
है ना?
Yes, sir. Thank you, sir.
Sir, in case of MOS capacitance, can we?
So Shivam, एक मिनट. Madhur also had raised his hand. पहले उससे बात कर ले.
Yeah. Okay.
Madhur?
Yes, sir. Sir, why does so when we draw the band diagram in presence of an electric field, the Fermi level was constant throughout. But why? But I saw in the book that Fermi level also changes with application of electric field. So why it is fine that Fermi level of silicon dioxide and p-type semiconductor is matching at the interface, but beyond interface, why isn't it changing with? I mean,
so when the Fermi level changes, it means there is going to be a constant flow of electrons.
Yes, sir. Yes, sir. Yeah.
है ना? तो हम तो अभी तो हम एक कैपेसिटर की बात कर रहे हैं जहाँ पे चार्ज तो अंदर बाहर कहीं जा ही नहीं रहा. There is no movement of electrons anywhere between the so up, if I have to give a gradient to the Fermi level also, then
Yes, sir.
there will be natural movement of electrons also continuously in that direction.
So, but we have also given gradient. We have already given gradient to EC and EV, but
No. That is an inbuilt gradient. After, in a static condition, suppose you are not applying this AC. If you were not applying this AC signal, what would happen? Would there be any flow of electrons here?
No, sir.
That is what. In the DC condition, there is no flow of electrons. Fermi level represents that. Therefore, Fermi level remains constant. And you have band bending.
Yes, sir. So band bending is fine, but I am not able to correlate why Fermi level is related to flow of electrons.
So that is how it is defined. It's a hypothetical term, Madhur.
Okay, as it's the definition I know is that around Fermi level, the probability of finding electron is half.
So let us look at it like this. यही देखते हैं. So let us say Fermi level is moving like this. So what are you saying? Over here, the probability of finding an electron is higher than the probability of finding an electron here.
Yes, sir.
So what happens? An electron comes here, it will naturally
Yes.
drift there.
Okay. Yes,
Nahi?
so yes, sir, yes. Okay, got it. So electron flow is necessary if there is a gradient.
If Fermi level has a gradient, then electron flow is inbuilt into it. It is implicit.
Okay, sir.
We are saying there is no electron flow happening in a DC condition over here.
Yes, sir. Yes.
So Fermi level cannot change. Fermi level has to be flat.
Okay, sir. Got it. Thank you, sir.
Okay. Yes. Samyak.
Sir, do we
Samyak,
utilize?
एक मिनट शिवम ने ना पहले एक सवाल पूछा था, मैंने उसको रोका था. पहले शिवम का सवाल देख लें.
Yeah, sir. Actually,
हाँ.
sir, previously in one of
Yes,
the
Shivam.
question, one of the guy was saying that about inversion layer in case of MOS capacitance. So, sir, as you have told that inversion layer formed when electrons from the source or drain region come on the surface.
In
So,
a
is
in
it
a
even
MOS transistor. In a MOS
yes, sir,
transistor.
MOS transistor, sir. So is it even fair to talk about inversion layer in MOS capacitance?
Yes. Why not?
Sir, because you told that inversion layer formed when the electrons from the source and drain come on the surface, as there is no source and drain. So
No. I never said electrons from source and drain come on the surface for formation of inversion layer. Only definition of inversion layer I gave was that the region that so when the band bending at the surface happens so much that you are only phi away. So if this was phi, you are only phi away from the conduction band instead of the valence band. So you become
sir,
as n-type as your p-type.
sir, the region
That is when
near
inversion
the
has happened.
oxide
That was the
interface
definition
is
of inversion I gave.
inverted. Sir, in this case,
Yes.
sir, that inverted region will have some depth.
No.
Sir,
Inverted. Okay. So inverted region has some depth, but there are no charges there. Inversion layer is only at the surface. So obviously this inverted region has depth. ये जो क्या कहते हैं जो ये band bending हुआ पड़ा है, this band bending has depth. You were gradually becoming less p-type, and you were gradually becoming more and more n-type. The moment you become as n-type
Yes, sir.
as your p-type, you say no more band bending will happen.
Yes,
so
sir.
at the surface, this is phi. After beyond the surface, this is phi plus.
Yes, sir. Yes,
Further
sir.
beyond the surface, it is phi plus plus.
Yes, sir.
Further beyond, it is phi plus plus plus, and so on.
So the complete inversion occurs at the interface.
And at the surface.
Yes, sir.
So Samyak.
Yes, sir. Do we utilize this property of changing capacitance in a MOS capacitor, like maybe to make a RC filter or something like that, where we need to
So if
control
we
the
can,
capacitance?
if we can utilize it, we should. But typically, we don't want capacitance. See, look at it like this. There are so many other things which are already varying in any electronic circuit. Threshold
Yes, sir.
voltage is varying, it is variable. There are other variations because of length and etching and so many things that are happening.
Yes, sir.
So there are so many things that are varying. Then you cannot, as a designer, you do not want to add additional sources of variations which are not in your control. So you would usually want to bias your circuit at one place and then design there. So if in analog circuit design, are you doing the CMOS course?
No, sir.
No. So in analog circuit design, the first step is to establish the bias voltage.
Okay, sir.
Then you do anything else.
Yes, sir. Got it.
Okay. So yes, if we take up a research project and we somehow decide to utilize this inbuilt variation, we can do it and we can explore it. But it is not usually the case. In an industrial setting, that is not usually done. You want things to be under control.
Okay, sir. So we characterized all this just to establish a biasing point and
yes.
Okay,
yes.
sir.
Okay. Yes, Shivam.
Sir, when we started talking about this MOS capacitance, sir, you told that MOS capacitance is very different from the normal capacitor. Sir,
yes.
Since now we have studied on these various properties of MOS capacitor, so but still it is a capacitor. We can so is it these properties are beneficial for us or?
See, unless you know this property, you will not be able to use a MOS capacitor. Are you aware? Are you able to see this?
Yes, sir.
So If you think that I will want to use a MOS capacitor and somehow you operate in a near threshold voltage of operation, then due to variations, your capacitance will vary significantly. Are you able to see this?
Yes, sir.
So it could be anywhere. It could go low, it could go high, it could go anywhere.
Yes, sir.
So you do not want to enter into this zone. Therefore, to characterize the MOS capacitor is very important.
Sir, since this MOS capacitance is very much sensitive to the operating voltage,
And
so
also frequency. Okay.
yes, sir. So won't that be better if we use simple capacitor?
Yes, or then you add source and drain region there. If you add source and drain region, then what happens? Then this curve goes away. This is the only curve. Low frequency curve is the only curve, because then what you are saying is that there is some, cache of electrons available over here itself. Electron does not need to go all this long distance, so यहीं से ले लेगा charge.
Yes, sir.
जो मैं छोटे वाला arrow बनाया था, it meets the specification.
Yes,
है ना?
Yes, sir.
So then at least frequency से independent हो गए आप. ये dependence फिर भी रही, लेकिन frequency से independent हो गए आप.
Yes, sir.
So अगर आपको bias point तो anyway बहुत सारी और चीजों के लिए establish करना ही है अपने circuit का.
Yes, sir.
So you can do it. So see, MOS capacitors are much denser than even MOS transistor capacitors are much denser than metal capacitors. Why?
Yeah, small size, sir.
Why can they be drawn in small size? That is the question.
Sir, we can have many capacitors on the same substrate.
Why? I want to make a capacitor of 1 picofarad. If I implement it by using a MOS transistor capacitor or a MOS capacitor and operate it in accumulation region, let us say, I will need an area of, let us say, 10 micron square. Whereas if I have to implement it by using metals, I will use an area of 200 micron square. Why this?
Sir, due to dielectric.
Dielectric is silicon dioxide in both the cases.
Area and sir, thickness
of
dielectric and the depletion region.
See, मैं तो accumulation में operate कर रहा हूँ, तो depletion की बात ही नहीं कर रहा.
Yes, sir.
So we're talking about thickness of the dielectric. In a MOSFET, this dielectric thickness is, हमने कितनी बात करी थी?
Around 10 angstrom, sir. Like
1 to 2 nanometer.
1 to 2 nanometer, yes, sir.
है ना? Or when you talk of two metal layers, what is the minimum spacing you have to keep between them in 65 nanometer? At least 16 nanometer?
Yes, sir.
Are you with me?
Yes, sir.
So if you see the gap in dielectric thickness,
yes, sir,
it is 30 times, let us say. So no wonder you need 30 times more area when you implement a metal capacitor for the same value.
Yes, sir.
है ना?
So it is coming from the foundry thing, basically, how it is manufactured.
Fabrication. So why do you think I talked to you about fabrication? It was not just to give you general knowledge.
Okay.
Because everything is linked.
Yes, sir.
है ना? So even when I'm talking to you about these capacitors and everything, this is not for your general knowledge. I'm not giving you something which is exotic. I understand that you will not become a good DVD designer, digital circuit designer, if you do not understand these concepts. That is why I'm giving you these concepts. This is not just because you did not cover or you may not take SSD course, therefore I am telling you. Whether you take SSD or not, this much you should know to become a good designer, to be able to connect the dots.
Yes, sir. Now I understand, sir.
Yeah, so don't think कि इस course में कुछ भी बताया गया है just for the heck of it. No, nothing. Whatever we are covering is important to be able to connect the dots at some point of time. That is what higher order thinking feels. Yes, Madhur, you had a question.
Yes, sir. So when for MOS capacitor, yes, a MOS capacitor, when we ground body and gate, then we give the reason for band bending as satisfying those electron barrier, 3.1 volt electron barrier, and matching the Fermi level. But when the gate voltage is not zero, then do we say that band bending happens also because we need to satisfy the shifting of bands due to the applied electric field?
Yes. So मैंने बताया था, याद है? You remember I told that I had mentioned once that we would use high K metal gate dielectrics and we could pin the VT to some level. I could modulate the VT of the device. So that is what you will do. What do you mean by modulating the VT? You will modulate the band bending. So
Yes, sir,
without
yes.
applying any voltage, there is some band bending that is inbuilt. So now additional voltage that you need to apply to get that 2 phi of bending is different, and therefore your VT could be higher or lower.
Yes, sir.
है bang on,
Yes, sir.
Madhur.
So,
Very good.
yes, sir. So this is also a reason for band bending, right? So we need to satisfy the electric field condition for changes in band bending due to electric field.
So the reason of band bending is that your Fermi level of the silicon region is not matched with the Fermi level of the metal region.
Yes, sir. That is. Yes, sir.
So
That
that
is
has
a
to be
general.
matched because there is no flow of electrons that is going to happen.
Yes, sir.
So it means there has to be some potential drop somewhere.
Yes, sir.
That's it.
Okay, sir. And additionally, when there is an electric field, external electric field applied, then also, because at some point, if we apply reverse electric field, bands also become flattened, right? So we do have to give a reason that because of external electric field also, we need to satisfy.
So अभी तो हमने external electric field की बात ही नहीं की, अभी तो हम internal electric field की बात कर रहे हैं.
Yes, sir. When there is no volt, we have not applied any gate to
In
gate
fact,
body
you apply
voltage.
voltage, band bending would change, but yeah, it's okay.
Okay.
है ना?
Yes, sir.
Okay. Yes, Teja?
Sir, actually, I'm not able to understand this. Band is bended for 3 point electron volts. Is there? No, sir?
So look at it like a fence. I say that the fence is. So you've seen photos of Great Wall of China?
Yes, sir.
So they are made on a mountainous trek.
Yes, sir.
So I say that the minimum height of the wall has to be 3 meters from either side.
Yes, sir. Okay.
So that is what we are doing. That is the property of the dielectric. It is 3 electron volts higher than silicon. That is the barrier height of a dielectric.
Sir, can I share one slide, sir? Because
Yeah,
I have done.
Teja, you're sharing something?
Yes, sir. Yes, sir.
Okay. Yeah.
Sir, actually, if you see left figure, sir, this one. This is about a work function, sir. It is not electron affinity. This is about work function. Sir, we have taken the reference over here, sir, actually.
That is the Fermi level. So I have already said Fermi level is going to be flat.
Okay,
if there is no voltage applied.
Yes, sir. If you are going to take the electron affinity, then this should be the reference, no, sir. Here, from here, it has to be taken.
Yeah.
From here to here, this will be 3.1 electron volts. If you are going to calculate from here also, then it will be somewhere here, because here only bending will happen.
Wait. Where is it said that phi m and phi s are 3 electron volts over here?
Sorry, sir.
So where is this 3 electron volts in the left figure coming from for you? How do you say that Q phi s is equal to 3 volts? It is not said there anywhere.
Actually, I am saying that if you're going to from the right figure, sir, if you're going to take a 3.1 electron volts, from here we have to take, no, sir,
from the conduction band to the barrier. That is the barrier height.
From EC to
the other EC. So if an electron has to move from silicon dioxide, from silicon to silicon dioxide, it will need 3.1 electron volts of energy. If an electron in conduction band of silicon has to move to the conduction band of electron of silicon dioxide, 3.1 electron volt of energy is required. That is the physics. That is the law.
Yes, sir. From here to here, I can say that 3.1 electron volts.
From here to here, नहीं. जहाँ पे arrow बना हुआ है, yes. Yeah, exactly. At the surface, 3.1 electron volts has to be there between the conduction band of dioxide, silicon dioxide, and silicon.
Actually, I have that because from here only we are going downward.
From where only? You're starting band bending in the entire depletion region. That is all a depletion region, is it not?
Yes, sir.
But the surface property is, so look at again. It is at the surface. When an electron wants to go from silicon, so an electron is coming from wherever, from the body, and it wants to go straight. It comes to the surface. There are so many electrons in the inversion layer. Why are there so many electrons in the inversion layer? Why could not they go on the other side? Because they encountered a barrier of silicon dioxide, which was 3.1 electron volt high. And that kind of voltage was not available. So those electrons all, kind of formed an inversion layer over there only. Does it help, Teja?
Actually, somewhat doubt is coming, sir, because I am thinking that if let's take this as a electron affinity means, let's take it as electron affinity means from conduction band to infinite.
Okay.
From here also infinite. From here also it will be infinite. From here also it will be infinite. Here only band bending is going to happen. So then it will be less than somewhat less than infinite.
Somewhat less than infinite, matlab? Anything less than infinite is also infinite, no?
No, sir. If you are going to take infinite as EC, in that case, then it will be less than this one, no, sir. Less than this
you can find 20 ways to confuse yourself, Teja. I am giving you one way to simplify it for you.
Okay, sir. Okay.
There can be hundreds of ways to confuse yourself. You can go and explore all of them. I am giving you one way, which is that keep it simple.
Okay.
Realize there is a barrier, and that barrier height is 3.1 electron volts.
Okay, sir. Okay, sir.
Can you accept this much?
Yes, sir. Yes, sir.
Then your life is simple. If you want to confuse yourself, go confuse. How can I help then?
Okay, sir.
Okay.
Yes, sir. Yes, sir. Got it.
Okay.
Yes, sir.
So I think that would be the last question. We are at the kind of end of our office hour.
Okay, can I ask one?
Thank you, guys. All the best.
Thank you, sir.
See you in the class on Wednesday. Okay.
So,
Yes, Saksham.
So can you stay back for 5 minutes? I need to discuss something.
Saksham, I have a meeting at 6.
Okay.
I'm sorry.
Okay.
We can meet at a different time.
Do you want me to schedule a meet?
Yeah, just ping me and we can work out a time. Okay.
Okay.
Yeah. Thank you. Bye.
Okay.
All the best.